What if falling into a black hole wasn't instant death, but something much, much stranger? We often think of them as cosmic vacuum cleaners, giant mouths in space that swallow everything, ending all stories. But the universe is rarely so simple, so final. What if the end of your journey into darkness was actually the beginning of another? Imagine a place where the familiar rules of time and space don't just bend, they completely shatter. A place where your future could become your past, and your past could be stretched into an eternity. This isn't just science fiction, it's a genuine question that sits at the very edge of our understanding of the cosmos, a puzzle written in the language of gravity and light. Before we take the plunge, let's pause and consider what a black hole actually is. Forget the idea of a simple hole in space. It's more accurate to think of a black hole as an incredible amount of matter, an immense mass, squeezed into an impossibly small space. Imagine taking a star many times more massive than our sun, and crushing it down until it's smaller than a city. The gravity of this object would become so overwhelmingly powerful that nothing, not even light, the fastest thing in the universe, can escape its grasp. This is the essence of a black hole, a region of space-time from which escape is impossible. The boundary that marks this point of no return is called the event horizon. It isn't a physical surface you could touch, it's more like a shadow's edge, an invisible line drawn in space. Once you cross the event horizon, your fate is sealed. The gravitational pull becomes infinite, and all paths lead in only one direction, inward, toward the center. It's like being in a river that is flowing faster than you could ever hope to swim. No matter how hard you struggle, the current will carry you downstream. At the very center of the black hole lies a point that defies our current understanding of physics, the singularity. Here, all the mass that fell into the black hole is thought to be crushed into a point of zero volume and infinite density. Not all black holes are created equal. They come in different sizes, each with its own unique origin story, much like the stars themselves. The most common type is the stellar mass black hole. These are the cosmic remains of giant stars, stars that were at least 20 times more massive than our own sun. When such a star runs out of fuel, it can no longer support its own immense weight. Its core collapses catastrophically under its own gravity, triggering a spectacular explosion known as a supernova. While the outer layers of the star are blasted out into space, the core continues to collapse inward, crushing itself into a black hole. Then there are the giants of the black hole world, the supermassive black holes. These are the true titans of the cosmos, with masses ranging from millions to billions of times that of our sun. We believe that one of these monsters, named Sagittarius A, lurks at the very center of our own Milky Way galaxy. We don't see it directly, but we can see its effects, watching stars whip around it at incredible speeds. Beyond these two confirmed categories lies a more theoretical and elusive type, primordial black holes. According to some theories, these tiny black holes might have formed in the chaotic, ultra-dense conditions of the very early universe, just moments after the Big Bang. If they exist, they could be incredibly small, perhaps with the mass of a mountain compressed into the size of an atom. Our journey continues. We are now approaching the black hole, and the universe around us begins to warp and twist in beautiful and terrifying ways. The first thing you would notice is the light. The black hole's immense gravity acts like a powerful lens, bending the light from distant stars. The star field behind the black hole would appear distorted, as if viewed through a giant cosmic magnifying glass. You would see multiple images of the same stars, their light bent around the black hole on different paths to reach your eyes. This phenomenon, known as gravitational lensing, is one of the ways we can detect black holes from afar. As you get closer, another stranger effect begins to take hold. Not on the space around you, but on time itself. According to Einstein's theory of relativity, gravity warps time. The stronger the gravity, the slower time passes. For you, falling towards the event horizon, your clock would seem to tick normally. But for an observer watching you from a safe distance, your journey would appear to slow down dramatically. They would see your spaceship get closer and closer to the horizon, but never quite reach it. Your image would appear frozen in time, redder and dimmer, stretched across the edge of forever until you fade from view completely. From your perspective, however, the opposite would be true. As you look back at the distant universe, you would see time speeding up. The moment has arrived, you are now at the event horizon. This is the invisible boundary we spoke of earlier, the point beyond which the gravitational pull is so strong that the escape velocity exceeds the speed of light. It is the ultimate point of no return. For a giant supermassive black hole, crossing this threshold might be, well, surprisingly uneventful. Once you are inside the event horizon, the nature of space and time fundamentally changes. Outside the black hole, you have freedom of movement in 3 spatial dimensions, up and down, left and right, forward and backward. You can move in any direction you choose, but inside the horizon, space itself is flowing inward faster than light. The direction inward toward the singularity is no longer a direction in space. It becomes a direction in time. It becomes the future. Just as you cannot stop moving into your own future, you cannot stop moving towards the singularity. All paths, all possibilities now lead to the center. Trying to fire your rockets to escape would be as futile as trying to travel back to yesterday. From this point on, you are completely cut off from the rest of the universe. No signal you send, no cry for help, no final message of discovery can ever cross back over the event horizon. For a smaller, stellar mass black hole, the end comes much more violently. Instead, you would experience one of the most gruesomely descriptive terms in all of science: spaghettification. This process occurs because the gravitational pull of the black hole is not uniform. The part of your body closer to the singularity is pulled much more strongly than the part that is farther away. For instance, if you were falling feet first, the gravitational force on your feet would be exponentially greater than the force on your head. This difference in gravitational pull, known as tidal forces, would begin to stretch your body. At first it might feel like a gentle tug, kind of like being on a medieval stretching rack. But as you accelerate towards the center, the forces would increase astronomically. Your body would be elongated, pulled longer and longer, thinner and thinner. The same forces would also be acting from side to side, squeezing you. You would be simultaneously stretched and compressed, drawn out into a thin, long stream of atoms like a piece of spaghetti. This process would not be limited to your body, your spaceship, the very atoms that make you up. Everything would be subjected to these immense tidal forces. Molecules would be torn apart, atoms would be stripped of their electrons. Eventually, you would be reduced to a fundamental stream of subatomic particles flowing into the singularity. But what if the story doesn't end there? What if the singularity isn't a point of infinite density, but a gateway to somewhere else? This is where physics moves from the known to the speculative, venturing into the realm of beautiful and unproven ideas. One of the most famous of these is the concept of a wormhole, also known as an Einstein-Rosen bridge. This theory suggests that a black hole might not be a dead end, but could be one mouth of a tunnel through space-time, connecting our universe to another point in space, another point in time, or perhaps even another universe entirely. If this were true, falling through the event horizon would be the beginning of a transit through this cosmic shortcut. Instead of being crushed at the singularity, you would travel through a theoretical throat and emerge somewhere else. The other end of this wormhole is sometimes imagined as a white hole. A white hole is the theoretical opposite of a black hole. While nothing can escape a black hole, nothing can enter a white hole. It would be a region of space-time from which matter and light are constantly erupting. You would be ejected from the white hole, a cosmic castaway in a new and unknown part of reality. However, there are significant problems with this beautiful picture. According to our current understanding, any wormhole that formed naturally would be incredibly unstable. It would collapse in on itself the instant anything tried to pass through it. To keep a wormhole open, you would need a form of exotic matter, with negative energy or negative pressure, something we have never observed and don't know if it can exist. There is another way the classical story of destruction might be wrong, and it comes from the other great pillar of modern physics, quantum mechanics. Quantum mechanics is the theory of the very small, of atoms and particles, and it paints a very different picture of reality from Einstein's theory of gravity. One of the fundamental principles of the quantum world is that information can never be truly destroyed, but a black hole, by swallowing things and leaving only mass, spin and charge behind, seems to do just that. The late Stephen Hawking proposed a solution with his discovery of Hawking radiation. He showed that, due to quantum effects near the event horizon, black holes are not completely black. They slowly leak a faint glow of particles, causing them to evaporate over immense timescales. One idea, known as the holographic principle, proposes that all the information about the three-dimensional interior of the black hole is somehow encoded on its two-dimensional surface, the event horizon. Another radical idea, called the firewall hypothesis, suggests that the event horizon is not an empty, peaceful place at all. It proposes that to resolve the paradoxes, the horizon must be a violent, high-energy wall of fire that would instantly incinerate anything attempting to cross it. So what truly happens when you fall into a black hole? Are you stretched into spaghetti and crushed in a singularity? Do you travel through a wormhole to another universe? Is your information scrambled and stored on the event horizon like a cosmic hologram? Or are you instantly vaporized by a wall of fire? The honest answer is, we don't know. And that is perhaps the most exciting answer of all. The black hole represents the edge of our knowledge, a place where our two most successful theories of the universe, general relativity and quantum mechanics, fail to agree. This mystery is not a failure of science. It is the very engine that drives it forward. The paradoxes and puzzles presented by black holes force us to seek a deeper, more complete theory of nature. They tell us that our understanding is incomplete, and that there are new, undiscovered principles of physics waiting to be found. Every observation we make of black holes, from the gravitational waves detected by LIGO as two black holes merge, to the incredible first-ever image of the event horizon of the supermassive black hole in galaxy M87, provides another clue. Each piece of data helps us test our theories and chip away at the mystery. We may never be able to send a probe inside one, but by observing them from afar, we are slowly learning their secrets. We are using light, gravity, and mathematics to peer into the darkness. The journey into a black hole is, for now, a journey of the mind. But it is one of the most important journeys we can take. It pushes the boundaries of our imagination and our intellect. It reminds us that the universe is not only stranger than we imagine, but stranger than we can imagine. The black hole is a dark and silent sentinel, holding the answers to some of the deepest questions we can ask about space, time, and our own existence. And as long as it remains a mystery, it will continue to inspire us to look up at the stars and wonder,